Open almost any astronomy textbook. Beneath the photo of the sun is one number students read once and forget: 5,800 Kelvin, the temperature of its visible surface. NASA uses it. The European Space Agency uses it. Every standard solar model starts there. It looks settled, boring even. Then, one line later, the physics breaks. Just above that surface, a thin, pale atmosphere doesn't cool down. It surges past 1 million degrees. Move away from the sun's surface, and the plasma gets hotter. That should not happen. Yet for 80 years, this contradiction has resisted 3 space agencies, a 4-meter telescope, and some of the best solar physicists alive. The distance that matters isn't between Earth and the sun. It's the razor-thin climb above the sun's surface. Just 2,000 kilometers up, the chromosphere is already burning near 10,000 degrees. Then comes the transition region, a boundary so thin it's almost nothing. Across it, the temperature doesn't rise gradually. It explodes from 10,000 to more than 1 million degrees. Beyond that, the corona stretches millions of kilometers into space. But the first proof that something was wrong didn't come from a spacecraft. It appeared during solar eclipses in the 1940s, when scientists split the corona's light into a spectrum and found signatures no known element could explain. Long before Parker's Solar Probe, Solar Orbiter, or the 4-meter telescope in Hawaii, astronomers had only eclipses and spectrographs. In the 1940s, those instruments detected something that didn't belong: faint, forbidden lines produced by iron stripped of most of its electrons, highly ionized states known as Phi-X and Phi-XIV. Iron could only produce those signatures inside plasma heated to 1 or 2 million degrees. That placed million-degree plasma directly above a surface measuring less than 6,000. It made no physical sense. Nobody had designed an instrument to solve the coronal heating problem. The problem didn't even have a name. There was only a stubborn fingerprint in the spectrum, one that ordinary hydrogen, helium, and the surface below could not explain. The anomaly was measured, logged, then left sitting in observatory records. Decades passed before scientists began building careers, spacecraft, and enormous telescopes around that single impossible signal. By the 1970s and 80s, the anomaly had a possible answer. Thomas Gold and later Eugene Parker proposed that the corona was being heated by nanoflares, tiny magnetic explosions, each releasing roughly 1017 joules, erupting by the thousands across active regions. The idea was elegant. It was also far from proven. Instead of ending the mystery, nanoflares ignited a debate that would consume the next 5 decades. NASA and the European Space Agency sent spacecraft after the missing energy. Solar Orbiter moved close enough to detect miniature brightenings nicknamed campfires. Parker Solar Probe plunged inside 10 solar radii to sample the corona directly. Then scientists built DKIST in Hawaii, a 4-meter telescope powerful enough to track the tiny surface motions that might be feeding energy upward. Billions of dollars, 3 flagship projects, 2 rival camps, wave heating versus magnetic reconnection. All of it grew from a strange line in a 1940s eclipse spectrum. And after 5 decades, the original mismatch remains. The cleanest explanation is wave heating. At the surface, boiling plasma shakes magnetic field lines like guitar strings. That launches Alfvén waves into the corona, carrying enormous amounts of energy. Inouye has measured enough energy in those waves to heat the corona and drive the solar wind. On paper, that could solve the mystery. But Parker Solar Probe entered the region where the simple version of that theory breaks down. Inside the Alfvén critical surface, the plasma becomes collisionless. Ordinary viscosity can no longer dissipate the energy. Then something called the helicity barrier intervenes. It blocks the energy from cascading to the smallest scales and redirects it somewhere physicists didn't expect, mainly into the ions. Protons become blisteringly hot. Electrons remain comparatively cold. Same plasma, same location, same moment. Wave physics can explain how the energy gets there. It still struggles to explain why that energy chooses one particle over another. If you enjoy investigations like this, subscribe, because this is the detail most coronal heating explainers leave out. Wave heating and magnetic reconnection disagree on the cause, but both expected the missing energy to reveal itself in the same critical region, the low corona, where the temperature spike begins. Parker's solar probe went there. What scientists expected to find was missing. Not everywhere, just where it mattered most. The missing evidence had a name: switchbacks. Parker's solar probe kept detecting these sharp, S-shaped kinks in the magnetic field, violent reversals that folded back on themselves like a cracking whip. For years, they looked like an ideal heat source. If magnetic fields were snapping backward again and again, each reversal could release energy directly into the plasma, exactly where the corona needed it. Then researchers tested that assumption across Parker's first 14 orbits. The result was devastating. Switchbacks were nearly absent in the low corona. They appeared much farther out, after the plasma was already flowing into the solar wind, too late and too distant to produce the heating they were supposed to explain. Think about that. Switchbacks are real. Parker detects them repeatedly. But in the hottest region, closest to the surface, they almost disappear. The leading suspect existed. It just wasn't at the scene. Then the mystery turned upside down. In the early 2020s, astronomers aimed DKIST, the 4-meter solar telescope in Hawaii, not at the million-degree corona, but back at the supposedly ordinary 5,800 Kelvin surface. At a resolution no previous telescope had reached, DKIST saw what others couldn't. Tiny vortices, barely 20 kilometers across, were spinning along the edges of concentrated magnetic fields. Scientists found 47 of them. They measured each one and matched its growth rate to simulations, confirming the first Kelvin-Helmholtz instabilities ever directly observed on the Sun. And these weren't harmless swirls. They were twisting and braiding vertical magnetic fields, creating exactly the kind of magnetic diffusion needed to explain how the Sun breaks down and rebuilds its field every 11 years, something classical plasma physics had never fully accounted for. For decades, physicists searched the corona's most extreme conditions for a hidden engine. DKIST found a possible engine in the most overlooked place of all. The surface everyone thought they already understood. And this is where one discovery splits into two completely different stories. Same 47 vortices. Two rival explanations. For the wave heating camp, these vortices may be the missing generator. They shake the magnetic field, launch Alfvén waves, and drive energy into the corona. That wouldn't replace the theory. It would reveal the machine powering it. But to the magnetic reconnection camp, those same vortices serve another purpose. They twist and braid the field until it becomes tangled, stressed, and ready to snap. They aren't the heater. They're the fuse for the nanoflares. Both interpretations fit what Parker's solar probe and solar orbiter have measured. Same vortices, same observations, two competing stories. And the only thing separating them may be the theory you believed before DKIST resolved the first swirl. Even without a final answer, these missions have already achieved something unprecedented. Every other star is just a point of light. Astronomers can measure its spectrum, brightness, and motion, but almost everything happening inside its atmosphere must be inferred. No telescope can resolve an individual vortex or magnetic braid on another star. The Sun is the exception. It's close enough to watch magnetic fields twist, follow energy as it climbs, and sample the plasma before it escapes into space. DKIST resolves the surface. Parker Solar Probe enters the corona. Solar Orbiter tracks the wider system. Together, they are building the first frame-by-frame record of a stellar atmosphere transferring energy from its surface into its corona. Not assumed. Observed. The evidence may ultimately prove wave heating, magnetic reconnection, or a combination nobody has fully modeled. Whatever the answer, no other star has ever allowed us to watch the mystery unfold this closely. The line in the textbook is still there. 5,800 Kelvin. Simple, precise, unremarkable. But above that number, the Sun is still doing something physics cannot fully explain. Vortices turn, Alfvén waves climb, magnetic fields twist, braid, and snap, releasing energy in bursts too small and too fast for any one instrument to capture completely. We can now see the pieces. We still cannot watch the entire transfer happen. Somehow, energy keeps leaving a cooler surface and entering an atmosphere hundreds of times hotter, just as it has every second since an eclipse spectrum first exposed the contradiction. The textbook gives us the number. The Sun still refuses to give us the answer. Thanks for watching.